Let's get started. Yes. Morning, everyone. Day 3 of the conference, last day. How's everyone feeling? Yeah, I know that feeling. They're going to close the door. This is the first conference I've been at, I think, where they close the doors on you during the talk. It's like, we're doing this in person and there's no way back out. Hello, everyone. My name is Kris Jenkins. I work for a company called Confluent, who are not the wiki people. We are the other one, the end in a T. It's a really, really awkward distinction. But we mostly concern ourselves with Kafka and running Kafka in the cloud. And so this raises the obvious question, which I hope you're here to get an answer to. What is Kafka? It's an interesting beast. It's interesting enough that it lured me in, and I ended up working for Confluent. But at the heart, it's really, really simple. It's a really simple idea. You take events, you take things that have happened in the real world, and you just write them down in a log, right? Someone does something on your website. A GPS thing sends you a location piece of data. Something comes from a process, and you just write it down in a log, right? Thing happened, and you keep adding on to the end. And you never go back and change what happened in the past. You just keep adding and adding and adding to the log as we go. Very simple idea, but I don't know if you've ever considered this, but logs are great. They have some really, really interesting properties as a data structure. First thing is, they're really cheap and fast to write to, because you only ever add to the end of a file. That's one of the cheapest file operations you can do, is just add to the end and just keep adding. You never go back and rewrite. They're also really easy to read. They're just a long file. You just go through, start to end, and you get all the data that happened, right? Because you just read them, you never need to because they're just written as a long log, and you never need to go back and write them, and you never need to go back and read what you've already read, they become really easy to replicate. You just copy what's happened so far. If you were to take a photo of this log, this list of 3 things, more people coming in. Pretend you've heard the bit I've already said. Just come on in and pretend I've already said it. Logs are great. People at the back, did you know logs are great? Right, you take a photo of this list of 3 things, it's a log. If I promise I'm never going to change that list, then your copy, your photograph, will never be wrong. It will always be right. The only thing it can be is slightly out of date, as I add a new thing to the end. Log files are really cheap to replicate. And they are great at showing you what's new. If you've ever gone to a command line and typed tail -f to follow a file, you know that log files are really easy to watch for the new events, for the new things that have just happened. So they make for really interesting data structures, and you'll find that actually, if you look inside pretty much any modern database, at the heart of it, there's a log because of these interesting properties of log files. If you look at the way most modern databases do replication, they used to do it really badly. They used to try and either sync individual blocks on disk, copy a block on disk to the other machine, and then it's already changed, so you need to go back and copy it again. And it really didn't work very well. Or they did the same thing at the table level and tried to copy rows, but then the row had changed by the time you copy it. It was a mess. I lived through that mess. We had a lot of downtime. The way most databases do replication these days is with a log. What they do is before they do any operation, they write down what they were going to do to a log file, just an append-only log file that keeps growing, and then they do the operation. And then the replicas are free to just copy that file. It never changes, it just grows. So it's a cheap, easy copy that can fail and resume where it left off. And you end up with this sort of thing, right? All the replicas are just reading from a log file, which they keep watching for new things and copying those. And then they build up the old state using their state machine. If the primary has the same list of events and is running the same state machine as the replica, which has the same list of events and the same state machine, they end up perfectly in sync. That's how database replication tends to work these days. And it's straightforward, and it works, and it survives the replication process crashing and coming back up really easily. So, what is Kafka? I think Kafka is the answer to an interesting question. If all databases start with a log, if all databases start with a state machine and end up building a log for replication, what if we started with a log file and then started building up our state machines on top of that? What would that look like? Would it look more like a database, or would it look more like a log file? We know it would probably be really cheap to write things to disk. We could expect writing to disk to be fast. We know it would be really easy to replicate if we started from that fundamental point. We know it would probably be really good at dealing with the new data, for watching for new things that have happened. But would it be a database? Or if not, what kind of beast would it be? This is one of my favorite questions to ask in the Kafka community, because it's always really polarizing, and I'm a little bit combative at times at theoretical questions. So I say to Kafka people, Kafka's a database. And they say, no, it's not. It's absolutely not a database. A database is tables and indexes, views, insert, update, delete, COD. Anyone old enough to remember COD, relational database theory? Just me. Amy at the back, you're doing a computer science degree. I expect you to learn about COD before the end of it, right? That's what a database is. It's MySQL, Postgres, Oracle, SQL Server. That's what databases are, right? Yes, but also no. I think our definition of databases has got a lot wider in the past 15 years, I'm going to say. We now accept that a document database isn't a relational database, but it is a database. We accept that key value stores are a kind of database. And I would say that Kafka is a database from a certain point of view. It just depends on your definition of database. And so I'm going to give you a definition of database, which I think Kafka fits in. I think a database is anything that can reliably let you store structured data and query it out in multiple ways. That's my definition of a database. I think that includes document databases and relational databases and key value databases and search-based databases. I think it includes Git. I think Git is a database. I think blockchain is a database. It may be a questionable business proposition, but I think it's a database. So this is the point I want to get to. What kind of database is Kafka? What is Kafka nature? Which is a really abstract question. And if you're anything like me, I find the way I learn the answer to abstract questions and the way I grapple with abstract concepts is to build things, to actually get my hands dirty and write some code. So let's build some answers to this question and then look back and see what kind of thing we've got at the end. When I decided to do this, I asked myself, what kind of thing should I build? I could build another Java pet store. The world needs one of those. I could build another to-do list manager. The world needs one of those. One thing that often gets done in the Kafka world is order processing, because it's important and interesting in real time. But I was a bit tired of that, so I thought it's a bit cliche. It's almost a cliche in the way the Java pet store is a cliche. So I thought I'd try and build something more fun, and I built a text adventure game. A couple of people smile. I know you played text adventure games in your childhood. I gave this talk once before, and I realized there are some people in the audience who won't know what a text adventure game is, which allow me to introduce you to another great concept in the history of computing, text adventure games. So they kind of survive today. They've gone out of fashion, but they kind of still survive today. If you look on the Steam store or wherever sells you your computer games, they kind of survive like this in narrative adventure games, right? You wander around the world, you talk to characters, you make decisions, and the story unfolds. Before the age of narrative adventure games, we had my own personal golden age of computer gaming, which was The Secret of Monkey Island, which it was a high point in human civilization. And this was the same idea, right? You would go around the world, you would find objects, pick them up, wander around the world, talk to people, eventually find the right place to use this object with that thing to progress the story. It's one of the few computer games of that era that was both massive and I actually completed. So before that, things were even less sophisticated. We had this. It was mostly text, few high-resolution images, to illustrate what's going on, but mostly you just type in things and get responses back. It turns out this is a really nice project to build if you're learning a new piece of technology or a new programming language, because it's just text. There's not much display work, but it does, as you'll see, exercise quite a lot of the system and force you to make some interesting design choices. So let's have a demo. Time for a demo, if I can find out which window my keyboard is reacting to. There we go. Okay. You make that a touch larger. Show you how this works, and then we'll break down how it's built. So, I have a prompt, I'm connected. I don't know what to type, so let me just type that. Unknown command, as for... I'm not going to try and pronounce that. Try asking for help. Okay, I'll ask for help. Available commands are look, go north, go south, go east, go west, pick up an item, use an item, inventory, and the help command we just typed. Okay, let's look. You are standing on stage at NDC Melbourne. It's not much of a stage, but the audience bask in the soothing glow of a terminal window. In the corner sits a computer noisily spitting out data. It needs to be processed, but you have no idea how to do it. You can see data and a lanyard. Okay. Why don't we try going west and see what's happening there? You step into the toilets. There's nothing to do here, at least nothing I want to describe. Okay, yuck. Let's go east again. Should we go east one more time? See what's happening? You're backstage. An old rock band is hiding here, refusing to go on. You look at their equipment with envy. You can see a microphone and a guitar. I don't think I need that. I'm going to go back west again. Okay. This is where the talk gets its title. I'm going to pick up the data. You pick up data. Let me check that. Inventory. Your knapsack contains some data. All right, okay. Let me pick up the lanyard. Yeah, let's just double check that. Yeah, now I've got data in the lanyard. Okay, let's carry on. Let's go north. You enter the main hallway. It is bustling with life and coffee. True, okay. Let me just try using a couple of those objects. Let me use my cat. You do not have that item to use. True, I cheated. Use the data? Can I use the data? You cannot use that item here. Okay, how about I use the lanyard? You wave your lanyard in the air like a fool. Someone in the distance shouts, "Hey, that looks like fun," and pretty soon you've started a flash mob of lanyard wavers. You dance for hours and then the party subsides, and as the mob leaves, the dancer drops his conference t-shirt. You pick it up. And if I just check the inventory, your knapsack contains data and a t-shirt. And so the game continues, right? That's how these games progress. You wander around, you grab items, you use them somewhere, and eventually you find your path through to the last golden item that lets you into the last golden location that completes the game. So that's enough of a demo. Let's see how it's put together. Quick warning, there is a lot of code we're about to fall into. And I do that for a couple of reasons. I think, firstly, if anyone wants to pause the video later and look through the code, you can. Or take screen photos now, that can be useful. Secondly, I think it's the way we communicate, right? It is our second language as programmers, code. So I actually like to see some code on a screen to show me what's really going on and what this will actually look like to build. I will say though, third day of the conference, don't get too bogged down in the code. It's the shape of the code that I'm really trying to show you. So just get the feel for how this is put together. That's what I want to communicate. So, how did I build this? I started off with two very simple logs in Kafka and a web server that would just write to them and read from them. So I've got a command log. Every time I type something, it goes to Kafka and it just gets appended to a log called commands. Something happens on the right, and then the web server is also watching a log called responses, which that something will write to. It watches that and sends it back out to the user. So if I did that, if I show you that as SQL, I define these two streams of data. The log streams are slightly interchangeable. A stream is the higher level thing that the log is using, right? It's a typed log. So I've got a stream of commands that's keyed by a user ID, which is just a UUID. And then I've got almost exactly the same stream of string responses. I just added a source on because that's slightly easier for debugging. But it's basically a log of things coming in and a log of things going out, keyed by the user that should hear them. And funnily enough, once I wrote this, I pretty much left the front end and the web server just running, because all the intelligent processing is happening on the back end at the Kafka side. And this is just a very dumb web server. So the interesting thing becomes, what do we do at do stuff? So let's start going with the simplest possible way of processing one log of incoming stuff into a log of outgoing stuff. We'll just do an echo server, right? If you've ever written any kind of back-end server to check the networking, this is probably what you did to make sure it was actually working. Hello, hello. In code, now this is Java. I know there are a lot of C# people here. There is a C# open source equivalent of this library I'm using. I've not used it, so I can't vouch for it, but I know it exists. You might want to check it out if you're more a C# person. So it looks like this. You create an object for building and working with streams of data, and you say, I would like to look at the stream of things called commands. I wonder if I can get my shadow up onto that. No, not quite, not that tool. You just tell it which stream of stuff you want, and you give it some information about serialization, which I'm going to gloss over. It's just like, this is how you serialize a UUID to binary and back. So just read it like this. We want to consume some commands and do something with them. And then once we've got that stream of commands as command stream, we can say, okay, map a function over it. You know, every time you get a new line, do something with that line. You're probably familiar with this from any kind of stream processing library that's making its way into just about every programming language these days. It's been in Python for ages. But it basically says, give me a function that can handle one element, and I'll turn it into a function that can handle the entire list. That's what mapping is. So what we do is just for every command we get, we build a string that says echo in that command. We tag it with the source for my debugging, and we stream that out to the responses thing. That's the simplest possible echo processor using Kafka and Kafka Streams in Java. So, with that infrastructure all in place, we can build out a game. We're going to need three things. We need to support general commands like the help and the I don't know what you just said, the as stuff I typed in at the start. We need to be able to move around the map and keep track of where we are and see the descriptions of the map. And we need to deal with holding and using items. So, for part one, for different commands, the first thing we need to do is split that stream of commands up into different kinds of commands we're interested in processing separately. So you do this, you say, you've got this thing that splits one log file into many sublog files, splits one stream into many substreams. And the way it does it is by testing it, and if you say, I'm looking for these kinds of things. If I return true, I'll handle it. Otherwise, let the next person in the chain handle it. You could call it an if, else if, else if, else if, else. Or if you want to get points in a job interview, you call this the chain of responsibility pattern. And the gang of four bless you from on high. So in code, that looks like this. You just call split on the stream. And then the game becomes, you are going to define a branch, you get a key and a value for that row, you return a Boolean, and if your Boolean returns true, you tell it how to handle the ones you've selected, and otherwise you let the chain worry about it. So our first real command will look like this. Have a look at the command, and is it equal to the string help? And if it is, then we do this. We just build up a nice long response string that you've already seen. When we type in help, it just spits out the help response. And we tag it with the source, and we string that out to responses, and we're done. The next bit, that's right at the top, then I'm going to show you the bit right at the bottom because it's the fallback. If none of our other processing works, then our fallback position, our final else, is just going to say unknown command. And then we build out the game in the middle by selecting different types of commands and processing them. So let's do some parsing. Another computer science classic. This is really, really basic parsing. It doesn't need much. So let's have a look at the directions first, moving around the map. Start with a list of valid directions. Go north, go south. And I'll just do this. If you give me if I'm allowed to test a key and a value, and the values command is in that list of things, then this is a movement command. I'm interested in processing it here. And I'm just gonna, instead of actually doing much work with it, I'm just gonna ship it off to a substream called movement streams, a separate log file, and I'll let someone else worry about it downstream. And this cracks open the possibility of doing processing all in one process, or as microservices that just route and shunt and transform later. Or I could do something a bit more fancy. I could actually start to properly parse the commands and split them out. So let me show you that. This is how we're handling the pick up and use commands. I'm just splitting the string into two parts, into a verb and a noun. And if the first part is pick up, then that's an inventory command. Or if the first part is use, that's an inventory command. And I can just, with that parsing object, that very basic parsing object, I can construct both my test, does it parse? And if it does parse, I can send that more structured object that's been split into two things, and I can create a stream of structured data downstream and send that off to inventory commands. So as a diagram, that will look like this, right? All the go north, go south stuff goes onto our movement command stream. All the pickup stuff goes onto our inventory command stream, and the rest we can just go straight back out to responses. So we're just building an architecture of stuff comes in, we think about it, we push it on somewhere else. Maybe it's going back to the user, maybe there's more to do with it first. But it's just stuff comes in, transform it, stuff goes out. So how do you do movement in that? Well, we've got all these movement commands, go north, go south, and what we'd like to end up with is the first thing that looks a bit more like a database. What we really want is a table that says the user ID and where they are in the world, right? So processing those go north, south, east, west commands into this is your place in two-dimensional space. So the first thing you do is I'm going to change all those strings into a delta. So north is x0 and y is 1. Have I done? I always forget which direction I've done x and y. Y is going up or down. North is up, right? Coordinates up. Turn it into, again, turning a string into more structured data, which is just a delta, and then we need to somehow roll up all those deltas by user to get their current position. Which you can just do like with this. You group it by the key, so we're just considering individual users, and then you reduce it by adding the x's together and adding the y's together. And that's how you make a table. That's how you roll up a series of events into a summary table that looks a lot like a regular relational database table. But the interesting thing about tables in Kafka is, yes, they're roll-ups, they're summaries, they're aggregates, but you can also treat them as streams in themselves. So every time this updates, we can get a notification coming out. We can tail a table for new changes. So as well as looking up where you are now, I can subscribe to alerts for when you move. And we can use that to announce where you've moved back to the user. To do this, just take that user's position table, turn it into a stream of new changes, and announce them back to the user as a position response, right? And actually, I'll show you this. I, over here, have, this is actually in the demo, I've just filtered it out on the UI, but all these position changes, there's one, you move to position 0, 0. They're all in the UI, I just hide them, but all these processes are running in the background. But you will notice the reason I've hidden them is that on its own isn't terribly interesting. You move to position 0, 0. What we really need is a description. So we need to somehow enrich these positions with a description of where that puts you on the map. We need to talk about locations, which introduces another idea in Kafka, which is, or in any database really, you need the idea of standing data. We need to draw a map and encode it and store it in the system. And they just start life off as a stream. Stream keyed by its XY position. We'll have a description of it, and we'll have the objects available as an array. And we'll just insert into it like this. So you're on a bridge, you're in a forest, you're at home with your television and fish. Good evening in. Right? And then we can build that up as a kind of standing data table with some code like this. Now this is more detail than I want to go into, but there are a couple of different kinds of tables in Kafka. You can have them sharded if you need to scale horizontally, or you can have a kind of table where there's a full copy on every single node. You need them for different reasons, but this is a small table, and I do want it available on every possible processing node, so I'm using a global table. And then with that, I've got two tables now. I've got one keyed by user ID that has a position, and one keyed by position that has all the data I need about where you are. I just need to join those and spit that out to the responses. And in code, that looks like this. Take the user's position table and turn it into a stream of notifications, so I'm reacting to changes. And then do a left join on the location data. When you do a left join, I will give you the thing that's user ID, where they are, and you have to tell me how to get the key of the thing you're joining to. So in this case, I just give you the position. I get the UUID in the position, and if I give you the position, you can left join, right? And then we get back the two rows that match, and we just munge them together into a Java object, which would look like neater code if we didn't have to do null handling, but we do, so it doesn't. Hooray. Nulls shall always be with us. No, I've tried to resist, but there are languages that don't have nulls, and it's really good. You know, we don't have to keep inventing languages with null pointers. We really don't. That's a rant for a different talk. Okay, where does that put us? Let me have a look. So now we have this stream of user location changes, right? We've joined it together, we've got the data. So we can just spit it out a response. Again, we're watching for nulls. You might have fallen off the edge of the map. I didn't do an infinitely sized map. You can walk off the edge if you want to, and we'll tell you to just run back where you came from. But it's pretty simple, right? This is mostly, again, mapping values to a stream, mapping a function to a stream of values and turning it into a string that goes back to the user. Congratulations, we built a walking simulator. This is, you know, we can walk around the world and we can see where we are. And if you don't play computer games, it may surprise you, but there are games where this is where they stop development and ship. There are some games that just walk around the world and read the lovely text. They may be great. I've never got them. It's not quite my definition of a game. If you like them, please tell me one that's good to get into first, because I can't get it. We need more than this to consider it a game, in my opinion. So, let's do that. Firstly, I have a feeling that user's I have a feeling. I've seen ahead to the end. I have a feeling that user's location stream is going to be useful later. So, we can turn tables into streams. Let's turn the stream back into a table. And the way we can turn that richer stream of user location data is to just group it by key again, and call that reduce function, but this time instead of adding the two together, we'll just forget the old one. Right? Once you move to somewhere new, forget where you were. So now we've got a table. We had a table of where you are. Now we have a rich table of where you are and what you can see and what the description is. We can work with that. That takes us to, we have live streaming data going around in a CQRS-style system. We can fan out the data and hand it off to other processes. We've got the notion of standing data. We have stateful tables, which give you live notifications when they change. We have joins. We've actually accomplished quite a lot by this stage. To finish off the game, we need to be able to pick things up, see what we've picked up, do our inventory command, and use the objects, and then we're done. So let's take those one by one, and we'll be good. To pick stuff up, I just looked at my watch. It's like 10 to 11. It's like, I've only got 10 minutes left. No, we started at 20 past. Thank God. Because those three things are going to take slightly more than 10 minutes to get through. Okay, picking stuff up should be easy. If you see the command pick it up, then check it's in the location. And if it is, spit that onto a new inventory stream, stuff you're actually holding. And if it's not, complain, right? As code, that'll look like this. Stream out the inventory commands, filter for where the action in our structured inventory command object is pick up, and join that to the user's location table. I told you it would come in handy, right? And if the item they're looking for is at that location, then create a new object called pickup, which says what you're trying to pick up and whether or not it's available. Right? So it's a request for the thing and whether or not it's going to work. And then from that, we can do our split processing trick again. We can split it out into the branches where it is available, and that's going to generate a new holding an item thing onto the inventory commands. And then a failure branch, which says it's not available, it's falling back to saying you can't pick that up. Right? That should do it, except we haven't let people know that they've picked something up, so let's just quickly do this. Every time the inventory actually changes, this is a real change to the inventory, not a request. Every time it actually changes, stream that out as a response. And that should look pretty easy by this stage. Stream out the inventory, look for the things where we're saying, yes, we're holding it, and turn that into a string to spit back at the user. So we can pick stuff up. How do we see what we're holding? The classic Dungeons & Dragons bag of holding. This introduces a slightly new concept of rolling up things into a state and then just adding new stuff to that state as it comes in. So in code, what we're going to do, stream out the inventory, group by the user ID again, and then say, okay, I start with an empty array, an empty knapsack. And every time a new holding an item thing comes in, I want to say, the computer's going to say, here's the current state of your knapsack, here's your array, here's the new thing, what do you do? Right? And I either add it in or take it out. So, in code that looks like this. We say, if the item's held and the current object available at that location are the item, then we just add it, if the item if we're trying to hold the item and it's not in your current list of objects, then add it, right? Otherwise, take it out. Again, this is one of these places where the code would be a lot simpler if Java were a little more friendly. For some reason, there's no good ArrayList.remove call. I don't know. C# fans, can you remove things from an array easily? Good, right, okay. I was horrified by this, but other than that bit being stupidly painful, it's just add it to the list or take it from the list, depending on whether they're picking it up or losing it. So we roll over, and we're just aggregating changes into our knapsack object and maintaining the state of that. Now that we have this knapsack that's keyed by user, we can do stuff with it, right? We can see what things we have. So look through the commands and find ones that say inventory. Join them onto the knapsack table, keyed by user, and then every time something happens that changes, every time someone says, what's my inventory, we can join to what they're holding and just spit back out the response. You know? I say inventory, we're already maintaining this array list of what you're holding, so we join and announce. We're almost there. We're almost there. We can pick things up, we just need to be able to use them, and we've got a game. But how do items work? Right? We need some rules. We need a table of rules for how items work. It's exactly the same as our map. We just create a standing data table and roll it up. So we say, Okay, we'll key it on the name of the item. We'll give it a position, a description, and when you use it, it generates some other item. Right? So you could do something like this. You can say there's an object called a drink. You can use it at position 5.8, and when you use it, I shall demonstrate live. This is how glasses work. Sorry, I'm thirsty. You take a drink and you're left with an empty glass, and then you'll get back the glass object, right? So it's a very simple standing data table of rules that we can create with that. And again, we use a global table, so the rules for every item are available on every distributed node. And then, I think we're almost there. We just need to do a whole bunch of joins. And we'll just build it up. And it's 3 steps we've already seen being pushed together in one system. So, if someone says use an X, join it to the knapsack, join it to their location, join it to the rules about the item they're trying to use, and then we can make a decision on whether or not this is going to work. So, stream out the inventory commands and filter for stuff where the action is used. Join that to the knapsack table, and I'll create an intermediary object called a pair. I don't know if you use Java, there's a tuples library which has pair and triple and, I don't know, quartet, quintet? I don't know how high I can go. But yeah, okay. So intermediary object, join that to the user's location, that gives you a triplet. Join it to the item rules, and finally now we'll produce a proper structured object, because those were just temporary objects for the join. And you end up, every time someone says use something, you end up with one of these records. It's got the inventory command, it's got the, that's going to have use and the noun. It's going to have the location the person is at, what they're currently holding, and the rules about the thing they're trying to pick up, all in one object. So we can branch on that and make our final decision. So split that up, right? And test it. The first test is it actually available here, right? Is it available? Is the thing they're trying to use actually in their knapsack? And if it's not, say you don't have the thing to use. We've seen that in the demo. Next test. Can you use it here? So check there's a rule for the item, and if there is the rules X and Y the same as your X and Y? And if they're not, say you can't use that item here. Stream that out to responses. If all those tests failed, then we must be able to actually use it. So we can just stream over and say, okay, you used the item, send that out as a response. You've got, and now we say, remove the old item from the inventory and add in the new item to their inventory and stream that out to the inventory thing, right? The only 2 pieces that are different about this code are, we're actually doing, because it fits on a slide now, we're actually doing 2 reactions to one event. When someone says use, we respond to them directly and to the inventory system in one piece of code, which is fine. You can respond to an incoming piece of data with 1 or more outgoing pieces of data. And indeed, we do a similar trick there because we're actually generating 2 different pieces of inventory data. You drop this and you pick this up thing in one piece of code. But again, the whole system is built out of stuff comes in, analyze it, make a decision, and stuff goes out. Something like that. Those are the streams we used. Data comes in, deal with it in real time, react to it, spit it out to another piece of data, and eventually the answer finds its way to the user. That's what most event stream programming ends up looking like, and that's what programming in Kafka ends up looking like. Data and decisions. So you could ask, is this a toy or is it a useful piece of code? And I think the honest answer is a bit of both. It's fun to play with technology, but there are actually a lot of patterns in use that work out into real world code. If you look at the inventory system, I think it doesn't take much imagination to see that as like a shopping cart. People add things to their shopping cart and remove them and eventually consume the whole shopping cart and it becomes empty. Inventory system in an adventure game is just like programming for a shopping cart tracking. If you look at the rules for the way items work, that's the backbone of building a workflow management system where rules allow different events to progress to the next level, the next stage. If you look at the way we've enriched the stream of users' position with the map data, you get something like parcel tracking, where you need to know not only where it is in the world, but what its status is. You need to join it with information about the depot, perhaps, to track items moving through the world, or a fleet of trucks moving through your delivery network. If you look at the way we've tracked people moving through the world, you've got the basis of an analytics command tool. You know, you can watch people moving through your... It's not that bad. Calm down. You can watch people moving through the world of a game, or you can watch people moving through your website and track what they're doing and generate intelligence based off those movements. So it's a toy, because it's a fun game, but it uses all the same patterns you can use in real-world work. And I think that's interesting. And you can build up tables and joins and a lot of the things you're used to in a real-time data streaming world. That's why I think Kafka's interesting. It's built up from the same foundation, but it builds up in a different way, and ends up in this kind of architectural system where data comes in, you deal with it, you make decisions on it, and you spit data out. It's actually, once you get used to it, a very simple programming model. And I also think it's an interesting part, if I can step back and see a bigger picture, I think it's an interesting part of the way programming is slightly shifting in the past, I don't know, 10, 20 years, I'm going to say. As to the point where we reached the point that processors stopped getting faster, data got more valuable, and storage got really cheap. We've started changing the way we program. Instead of saying, I'm going to build systems where data can change, data mutates, we do updates on data, and then our job is to protect it. We protect individual pieces of data with objects which guard from change. Or we build microservices that have a database and guard from you changing them and just proxy that access. Instead of programming like that, we say, well, facts are just facts. Let's just record them. They don't change. New facts come in. We just store them. We don't need to guard them because no one can change them. Have a copy. It's fine. All we need to do is take that data, make decisions on it, and produce new facts, right? You see this, I think you see this in the move in programming from object orientation to functional programming or immutable data structures. Instead of dealing with mutation and then trying to build up structures around it to cope with that mutation, don't do mutation at all. Store facts and build up systems on top of storing facts. I think that's the spiritual difference between object orientation and immutable functional programming. I also think it's the difference between doing something like jQuery, where we manipulate individual pieces of the DOM, and something like React and Redux, or Elm that inspired it, where you just have streams of facts coming in, you roll up and make a decision based on it, and you display that out to the user. I also think we do it in DevOps as well, where instead of having like individual Snowflake servers that we manage and manipulate individually, we just write something like a Docker file, which is a recipe of events that have to happen to your base state to generate a final state. I think this whole pattern of eliminate mutation, just record the facts and process those for new facts. So I get the sense this is sweeping through our industry, and I think this is, I think Kafka's part of that when you take that idea to persistence and databases. That's my hypothesis. I also think it's terribly interesting, so I hope you found this interesting. If you'd like to see some more code, I do have a video on YouTube which you can find, which is a complete walkthrough of building a Kafka-based system with a portable synthesizer, my music composition skills, which are kind of ropey, and a 3D graphics library, which goes into more code and more detail. If you fancy that, there's a QR code to it. That QR code will also take you to the source code for this project. It will take you to our company's developer resources for learning Kafka. It'll take you to the podcast that I host, if you're not sick of the sound of my voice already. Yeah, QR code. I hope you found that interesting. I will happily take any questions you've got. Thank you. Yeah.
What's the general pattern for querying that data? Let's say in your example, if you want to find all the users which have an item in their inventory.
So the question is, what would you do if you want to query for all users that have a particular item in their inventory, or just what your general query pattern? Generally, what you do is you would build up, you define a process that says, you do it two ways. If you're doing ad hoc, you would probably pick a point in time that was fairly recent and just roll forward through that history data and just scan through it. When you decided that was a useful query that you wanted to have fast and permanent, then you would create a process that transforms that list of inventory into something keyed by the item you're interested in, and contains the users that have that currently. That would remain live as new data comes in, and you can do fast key value access on it. So you can get ad hoc queries. Good on time. Okay. Thank you very much. I'll be around for the rest of the day. Please have a chat if you fancy it. Thank you.